So this one is a pop quiz which is related to topic waves. In the first question, light from a laser is incident at an angle of 90 to the reflecting surface. So this is a reflecting surface. Light from the laser is coherent. You have to learn the definition of a coherent. Coherent means like it has a constant phase relation. What does it mean? Like every time if the crest is coming out from the source, so all the waves have the crest every time. That means the constant phase relation is there. So how we define coherent source? The coherent source means the source which is having a constant phase relation or phase difference, you can say. That is known as a coherent. State why standing wave form between the laser and the reflecting surface. So what is the reason for formation of a standing wave? What will happen when two waves are traveling in opposite direction? They will give rise to a standing wave. So what are the two waves? One wave is from the source, another one is from the reflecting surface. So the source and the reflecting surface, these two waves, which like combined with each other, they interfere, and as a result of interference, it gives rise to a standing wave. So the two progressive waves moving in opposite direction give rise to the standing wave. So standing wave can only be formed or superimposed with each other when they are traveling in opposite direction. In question 2, a glass is filled with a transparent hydro beads. Hydro beads, when these beads absorb the water, the size changes. The glass is then half filled with water, and the beads under the surface of the water seems to disappear. Like as you can see, that the bead does not appear. The refractive index of the hydro bead is similar to refractive index of the water. That's why these beads appear to be disappear. Explain why hydro beads are difficult to see when surrounded by water. Because they have the same refractive index. So if they have the same refractive index, as a result, what will happen? The direction of the light does not change. If the two, for example, if two mediums have the same refractive index, example here, say a light is traveling from air to water, why the direction of the light changes? Because air and glass refractive index is different. But what will happen, say if there is a water and we have this beads also, and if this bead is having a same refractive index, so it will not cause any refraction, so it will pass, because as a density of a medium does not change, so it won't change the direction. So why the hydro beads are difficult to see when surrounded by the water? So first thing, because they have the same refractive index, so as a result, there will be like no change in direction of the wave. So same refractive index. So as they have the same refractive index, as a result of the same refractive index, the direction of the ray does not change when it changes a medium. So no change in direction. And if there is no change, and we can also see it, if some reflection will happen, that we can also see. But because the refractive index is same, so there is no reflection from the bead. As a result of a no reflection, we are not able to see the beads as well. So we remember, when two mediums, two different materials have the same refractive index, then the light will not change the direction. In part B, a ray of a light in air is incident on a damaged hydro bead, as you can see. The diagram shows a ray until it is incident on the damaged surface at position X. The refractive index of a hydro bead is 1.38. We have to calculate the angle of refraction. So what is the refractive index of the air? 1, and refractive index is 1.38. So we use the Snell's law, which is N1 sine theta 1, like refractive index of the first medium multiplied by angle in the first medium from the normal, refractive index of the second medium multiplied by angle in the second medium. So refractive index of air is 1, sine the angle from the normal we always take. So this is 42. Refractive index of the medium 2 is 1.38, and angle of the refraction we don't know. Just 1.38 will go there in division, and we'll take a sine inverse. So it will be sine 42 divided by 1.38. That will be equals to sine r. And if we need r, so sine will move other side, it will be sine inverse. So it is about 29 degrees. Whenever you solve a question, 1 mark is for writing a formula. So use the correct formula, write the formula. Complete the diagram to show what happened to the ray at position X. And your answer should include calculation. Now, first, if you want to complete, like here, it is moving from hydrobead to air. We have to check the critical angle. So how to work out the critical angle? N is equals to 1 over sine C. You can use here because air is there. Or you can also use a formula, the same one, N1 sine theta 1 equals N2 sine theta 2. Now, in this part, if the angle of the refraction is 90, we are finding the critical angle. You can use N equals 1 over sine theta or 1 over sine C, because the one of the medium is air in this example. But what if there was no air? Then you have to use again the concept of the Snell's law. So N1 is a refractive index of the first medium. Like now it is moving from hydrobead to air. So 1.38 sine, this angle is given 50, angle of incidence. Refractive index of medium air is 1, and sine theta 2 is actually, sine theta 2 will be 90. So we are finding the critical angle, like at what will be the critical angle? So that is unknown, C. So if I need sine C, sine 90 is 1, so it will be 1 over refractive index and then take a sine inverse. So if I need C, so it will be sine inverse 1.38. So sine inverse 1.38 will give you the refractive, the critical angle of this glass bead. So critical angle for this glass bead is 46. So now this angle is more than 46. So what will happen? Instead of light will go out, it will reflect back in the same medium. And you have to make the angle 50 degrees. So the calculation part, you have to work out the critical angle and then compare the critical angle with the angle of incidence. As in this example, the angle of the incidence is more than the critical angle. So light will undergo a total internal reflection. You can directly use N equal 1 over sine C, but that is only valid if one of the medium is air. But if we have any other, then we cannot use. In question 3, the photograph shows a musical instrument which is called a harp. The strings of the musical instrument are there. When a harp string is plucked, the transverse waves travel through the string, forming a standing wave. What is meant by transverse wave? So definition of a transverse wave, that in which the vibration of a is perpendicular to direction of the wave, or oscillation or vibration is perpendicular to direction of wave or direction of propagation of wave. And the other one is a longitudinal, in which the oscillation is parallel to direction of wave. So transverse means that its vibration is perpendicular to direction of the wave. For definitions, learn the standard definition. The diagram represents one string of a harp. The string is fixed at both ends. The string vibrates to the lowest. So lowest, what will happen? Always remember, for a string instrument, always at the end, it will form a note. So this will be node and this will be node. That's a minimum pattern, and this will be antinode. So how the pattern will appear? This is a minimum way it can vibrate, which is also known as the fundamental frequency or fundamental first harmonics. Add to a diagram, show how standing wave. For example, if this was a pipe instrument, so for a pipe instrument, open end, always it will be antinode. And if it is a closed pipe, the pipe which is closed from one end, so it will be node at the close end and antinode at the open end. So these are the minimum possible patterns. For this one is for open pipe, this one is for the closed pipe, and this is for the string, the lowest frequency, like minimum number of loops. Add to a diagram, and you should label any nodes and antinodes that we did. One string produces a sound with a frequency of 196 hertz. The wavelength of a wave in the string is 0.72 and the tension is 41. The string breaks and need replaced with a new string. The table shows the mass of the four new strings A, B, C, and D. Each string has a length of 1.5. The new string is cut to the same length as a broken string and then placed under the same tension. Deduce which new string A, B, C, or D should be used to replace the broken string. So we have the frequencies given and different strings are there, and we cut according to the original one. So the formulas, remember, for formulas for the string, the speed of a wave in a string is always given by V is equals to under root T divided by mu. Like T is the tension and mu is the mass per. And another formula, V is equals to F lambda, that is a wave equation. And lambda is in terms of length, depending on the fundamental frequency, like the number of the loops, the lambda will change according to that. And as well as the frequency will change. So first, using V is equals to F lambda. So frequency is 196. What about the lambda, the wavelength? The wavelength of a wave is 0.72. So we have 0.72. So we got what speed the wave will travel. So using V is equals to F lambda, we work out what speed the wave will travel. It is 141 meter per second. Now we will work out the mass per unit length. So V is equals to under root T divided by mu. T is the tension in the string, which is 41, and V is the speed, because we want the same speed. So 141 under root T, which is 41 divided by mu. So we square both sides and we work out to get the value for mu, the mass per unit length. So this will be 141 square and this will be, so 141 square is equals to 41 divided by mu. And if we need mu, it will be 41 divided by 141 square. So the mass per unit length will get 2.06 into 10 to the power minus 3 kilogram per meter. That's a unit of mass per unit length. Then after getting the mass per unit length, after getting, till now we got the mass per unit length. Now what mass is there? This is mass per unit length, like mu is equals to m divided by L. We need m, so mu will be multiplied. So mu will be multiplied by L, we'll get m. And each string they mention, that because this is a mass what we need. Each string length is there. It is 1.5. So mu we work out 2.06 into 10 to the power minus 3 multiplied by length of the string, which is 1.5. So when we multiply, we get the mass, which is 3.09 into 10 to the power minus 3 kilogram. So this is a mass that is in kilogram. We divided by 1000, multiply by 1000 to convert into kilogram, kg. So it will be 3.0, it is in kilogram. We want to convert into grams, so we multiply by 1000, so it will be 3.09. So that matches with 3.1. So that's why string B should be there. So that's how we worked out, like using the mass of a string. We work out. So the string is there. The each new string has a length. Like each of them is 1.5 meter, 1.5, 1.5, 1.5. And the new string is cut to the same length as a broken one and is placed under the same tension. So deduce the new string. So how we work out the new string? We work out the new string by from the mass, how much mass is there. Is it clear? In question 4, boat can shelter from wave on the in a sea harbor. The diagram shows a harbor where the boat can enter and leave, and the gaps are there. Waves on the sea are diffracted as they passes through a gap of the harbor wall. Describe how hygiene construction can be used to predict the shape of a diffracted. Look, what is the hygiene principle? Simple principle is that using one wavefront, like example, what is the hygiene principle? Using one wavefront, we can locate the position of another. Like if I know this is one wavefront, the another wavefront, if we draw small arcs, we get the position of another wavefront, the next wavefront. So using this one wavefront, we can find the position of another wavefront. That is the hygiene principle. So example, if this was a curve, then according to hygiene principle, how we can work out the new wavefront? So we mark, like using a compass and the wavelength, we mark and draw an arc, then another point on the wavefront which we have, draw an arc, another point, draw an arc. So by drawing arcs from the primary wavefront, we can work out the new position of the or position of a new wavefront, the secondary wavefront. That is the hygiene principle. So describe how hygiene construction can be used to predict the shape of a diffracted wavefront. So how we can identify that what will be the shape of the diffracted wavefront. So using the primary wavefronts, we can, or using the wavefront, using a compass, how it can be done. You have this wavefront, you mark a point, like using your compass, mark any points on your primary wavefront and draw the arcs. So when you draw these arcs will intersect, and when you join the point, the position where these arcs intersect, that will be the new position of the wavefront. But we don't have to construct that, we have to describe. So how we can use the hygiene principle to construct the secondary wavefront? So what we will do, we will mark the points or use the points on the primary wavefront to work out the position of the secondary wavefront. And the second thing, like how diffraction pattern can be. So the points, the diffraction hygiene constructs the wavefront. So we will mark the position or mark points on the primary wavefront. So using them, we can locate the position of secondary wavefronts. Is it clear? So each point on the primary wavefront, when we compare that this point is a source, like this is emitting out the wave. So if this is a wavefront we mark anywhere, you can mark the point on the primary wavefront. So you draw an arc. Then you draw another arc from this point. You draw another arc from this point. You draw another arc from this point. The position or the point where these arcs will intersect or meet, when we join that point, those points, we get a secondary wavefront. Is it clear, 4A? How to know the distance between them? The distance between them is the wavelength. So this, for example, if this distance is say 2 centimeter, so when we draw another arc, when we draw the arcs, the arc length should be 2 centimeter. Not arc length, means the how you can measure. So how you can measure, like just measure this distance between the pen and the pencil of your compass, and say this is 2 centimeters. So after knowing like this is a wavefront, the previous was 2 centimeters. So if you want to locate the new wavefront according to Huygens principle, how it can be done? Just 2 centimeter arc, 2 centimeter, 2 centimeter. Not this arc length is not 2. The spacing is 2. And then join them, you will get the result. The next is the wavefront in the sea arrive parallel to the harbor. The wavelength of the wave varies with as the weather changes. There are identical boats at two positions A and B in the harbor. As the wavelength of a wave vary, the boat A always oscillate at a large amplitude, and boat B sometime oscillate large amplitude, sometime very small. Look what will happen when the wave passes through this gap, the diffraction will happen or occur. Like wave will diffract and wave will diffract. But A is always the maximum will be there at A, because it is irrespective. At A, both wave covered the same distance. So as they covered the same distance, they will always have a path difference of 0. So when they have a path difference of 0, at 0 we'll always have a maxima. So A always experience a maxima as the wave is passing. But what happened to a B? B sometime maxima, sometime minima. What is the reason? Because when the wavelength changes, if, as you know, that if the narrow gaps, if the wavelength is approximately equals to the gap size, if this wavelength and the gap size are approximately equal, then only we'll have a maximum diffraction. But if this wavelength is shorter, then the gap size, like gap is larger and the wavelength is shorter, as a result, we'll have a minimum diffraction. This will be a maximum diffraction when the wavelength is less than the gap size. So why A always there will be a constructive interference, even any kind of diffraction, even a small diffraction or a large diffraction, the path difference between the two waves will always be 0. So how you will write your answer? You will explain your answer. First thing, you'll mention when the wave passes through a gap, it diffract, and these diffracted waves interfere with each other. And when the wave interfere, they will always have a path difference of 0 because they are covering the same distance from the gap. As a result, there will always be a constructive interference. But for B, what will happen? When the wavelength changes, the diffraction pattern changes. So there might be a constructive, and the path difference can change. So there might be a constructive interference or a destructive interference. So if it's a constructive interference, then it will vibrate at a higher amplitude. If there's a destructive interference, it will vibrate at a lower amplitude. So y is always a maximum diffraction because this distance from here to here is same. But what happened for B? This from one to other, the gap is not same. So they will have a part difference. And that part difference, if the part difference like lambda, 2 lambda, 3 lambda, then it will be a maximum oscillation. But if the part difference is lambda by 3, lambda by 2, 3 by 2 lambda, or 5 by 2 lambda, then it will be a minimum minimum or interference or a destructive interference, we can say. Is it clear? Question 4 part B. So you have to describe why the boat oscillate as it is described. And it's a 6-mark question. So your answer should be like you should relate one point with another. Like for example, you will mention when the wave is passing through a gap. It diffract. And the diffracted waves will interfere the interference pattern depends on the part difference. You can say superimpose as well. And the interference pattern depends on the part difference. At A, part difference is 0. So all the cases, it will have a maximum interference or a constructive interference. So it will vibrate with the maximum amplitude. But at B, the part difference changes because the wavelength change. So as the wavelength change, the part difference will also change. And at B, it will be maxima. It will be maxima if the part difference is lambda, 2 lambda, and at B, it will be minima if the part difference is lambda by 2, 3 by 2 lambda. So lambda, 2 lambda, 3 lambda, the wavelength, and here lambda by 2, 3 by 2 lambda, 5 by 2 lambda, and so on. So the distribution of the marks, how the marks are distributed, when you will mention about wave is passing through a gap, interference or superposition is there, then there is no part difference for A, and it will always be a constructive interference. For B, the part difference changes as the wave changes. It will be maxima if the part difference is multiple of the wavelength, and if it is a fraction of the wavelength, then it will be minima. Is it clear? This last question from the pop quiz of waves. Superposition or interference is the same thing which is used when two waves combine. We can say they interfere, or we can say they superimpose. So one wave combined with another, even they're moving in same direction or opposite direction, but they combine, we call it superposition, or we can also say interference.